Hello and welcome to another one of these ADD videos. Today we're going to be looking at this example and we're going to be using the epsilon delta definition of a limit to prove that the limit of this is indeed 0. So let's take a look at what we got going on here. So step 1 is to list the definition. We have f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. And this is all based off of limit as x approaches c of f of x equals L. So when we plug into the definition, we get f of x minus the limit is less than epsilon. There's our x minus c is less than delta. Our goal is to make this look like this. Well, typically we do some factoring or something like that, but here we gotta combine this expression with that expression. Let's form our common denominator and get that combined, and you'll see if we rewrite it. The common denominator is x, so I multiply top and bottom by x, and if we rewrite it over a single fraction, this is what you get. And I'm going to actually write them as a product of two terms so that I can see the x minus 1, the x minus 1 right here, and x minus 1 are the same. So this is the expression that I must bound. So usually what we do is we let delta equal 1, and then we try to create this, or we try to turn this into this, okay, by doing a little algebra. So we drop the absolute value signs, we get the same direction sign as this, and then put the negative of whatever number's here. In this case, we chose 1, so we put the negative 1 there, and then we try to create that expression. So if we add 1 everywhere, and then flip it to get the 1 over x, you see that we get this 1 over 0, and we cannot have 1 over 0 in our bound. So this is one of the rare times where we cannot let delta equal 1. We have to choose something else, all right? So in this case, we can choose a half, just get a little bit closer to the c value, and when we do that, this is what you end up with. So if we let delta equal a half, same process, drop the absolute value signs, we're going to get the negative in the same direction inequality. Then we try to create the expression from this that we have here. So we add 1 everywhere to get x by itself. Then we got to flip everything. Don't forget, whenever you take the reciprocal and there's an inequality in your expression, you also have to change the direction of your inequality. All right, so these were less than because I took the reciprocal of everybody. They're now greater than. Now we ask ourselves, which one of these numerical values is further away from 0? And it's 2 is further away, so we put the same direction inequality with a negative 2 on the other side, getting that there right here. And then after that, because we have the same number here and here, we can now bound it with the absolute value is less than 2. And that is going to be our k value. That's what we're going to replace this 1 over x by. So when we do that, we get that there, and then our goal is to just have x minus 1 on the left side so that we can compare these two equations. Actually, this one here with a delta. And because this is the same thing as this, then that means delta has to also equal epsilon over 2. Now, because you chose a delta of 1/2, we are going to have to write our answer in the terms of the min function, just like in the quadratic in the intermediate example video. And that's going to be a choice of the delta you chose, right? We chose a 1/2, and the one we solved for, epsilon over 2. So depending on what epsilon is, it'll choose this one or this one. So if epsilon's 4, between 1/2 and 2, 1/2 is smaller. But epsilon is 1/2 or 0.1, then epsilon over 2 would be smaller, and we'd choose that value. All right, I hope I've clarified things enough for you to practice a few of these. Make sure you check out the special case scenarios, including the trig ones. As always, practicing is the key to understanding. So practice, practice, practice. Thanks for watching and have a great day.